Alrighty, let's get started. Alright, so not very many people here for the live stream yet, but we got to do recording this anyway, because I got to get this up for my students so they can watch this at their leisure. So, where should we start? So 1 through 15. Looks like number 1 is going to be an example of addition, subtraction, multiplication problem, and explain it in 3 different ways and why those methods work. So for me, the easiest one I can think of is explaining subtraction and showing a couple methods for that. So obviously the regular subtraction algorithm is something like this. So let's do 42 minus 27. And the normal algorithm is going to be borrow from here, making this a 3, it's a 12. And really what's going on here is, if we're going to explain this, is that what we're doing is we're taking the problem 42 minus 27, and we're rewriting this as 30 plus 12 minus 27. And so here we're doing 12 minus 7. So you can think of 30 plus 12 minus 20 minus 7 is how this is being represented. And you can subtract these in any order. So what's happening here is 12 minus 7. So we're taking these two. And 12 minus 7 is going to give us 5. And then we've got 30 minus 20 is what these represent. Again, it's all about place value. So the 3 is representing a 30, and the 2 is representing a 20. So that's these guys coming together. 30 and negative 20 to give us 10. And so we drop a 1 here, because that 1 stands for a 10. 15 total, right? Once we put these together. So that's what the regular algorithm is doing. And this had some major flaws in it. First of all, if I wanted to subtract negative numbers, or I'm sorry, I wanted to subtract small from big from large. So if I were to flip this problem around, the problem here is that I can't really borrow. Oh, what's up, Perkins? I can't really borrow to help this out. I mean, you can talk about like there being an invisible like 1 or a 0 here, and you can borrow from that, make a negative 100 or something, right? But then we're going outside the algorithm that most people know. So here you can do 7 minus 2 and get 5, and then you're kind of stuck, right? But if you're comfortable going outside the algorithm, you can think, I can do 2 minus 4, which is just 20 minus 40, and get negative 20. And then if I combine these things, and again, combination is always addition, I get negative 15, which is the answer to this type of problem. So this way works fine, right? This is the way they teach you in like early elementary school. And what you're doing is you're breaking this problem down. Instead of 42 minus 27, when you borrow that 1, what's really happening is you're rethinking this problem as this. 30 and 12, 30 and 12, minus a 20, minus a 7, and then you're choosing which ones to go with, right? So that's one way to explain subtraction, is this basic algorithm. And you can kind of make it work, sort of doing it this way. So here's one way, this stuff. And here's the second way of showing how this works. I guess if you wanted to use the exact same problem, you could do 40 minus 20 is 20, 2 minus 7 is negative 5, and then when you put those together, 15. Avoids the whole borrowing nonsense, which is not a problem on paper, right? Borrowing and doing all this stuff, but like memorizing and remembering that you've borrowed and done all that in your head is really complex with like bigger numbers. Perkins, how are you? I'm making a video for my kids because most of them are not showing up for the live stream. That way they can watch this and get their final project done. I'm going through all the different things we've done since the beginning of the year. All 15 things. You know, a whole lot. How are you? How's the dog? How's the fam? So we've got one more way to talk about subtraction, right? You need 3 without a calculator and explain what's going on. Well, subtraction is just asking the distance between numbers. That's all it's asking. And that might seem sort of, kind of not really helpful, because it's like, okay, great, what's the distance between 42 and 27? Well, to figure that out, I'm probably going to subtract them in my head, right? But if you know that we're talking about distance, I'm doing okay. Obviously, cat's death isn't great, but doing okay. Hanging in there. So if I'm subtracting these numbers, if I know that subtraction is just asking the distance, as long as I move everything the same amount. So you can imagine 27, 40, 42, right? And if I scoot them the same amount to the left, notice how the distance doesn't change here, which means the answer doesn't change. And why is that beneficial? Because I can scoot this 2 to the left and make this 40. And I can scoot this 2 to the left and make this 25. And now I have a much simpler question. 40 minus 25. And that'll give me the same answer as 42 minus 27. And so knowing this, I can kind of count up easily from there if I want to. 5 more to get to 30, 10 more to get to 40, so the answer is going to be 15. Which is a little bit easier counting than this. Now, when it comes to double-digit numbers, and especially single-digit, this might not be super helpful, but this can be really helpful if you have large numbers, like 535 minus 472. And knowing, oh, I'm just chilling, man. Hanging out here with the cats and Abigail, staying home, trying not to get anybody sick or get sick myself. I think the plan is maybe to visit my parents like after, like close to New Year's, because then it'll be 2 weeks of me being home doing nothing, them 2 weeks doing nothing, and then my sister Kayla, who is basically a nurse, she'll be vaccinated by then, and so maybe we'll get together then, but we'll have to see. How about you? So I can rethink of these by moving them all down a certain amount. So I can move this down 35 and make this 500. So I moved it 35 to the left. And I can move this 35 to the left very easily. 70 minus 35 would be 35. So 72 minus 35 is going to be 37. And then I can just count up. 3 to get to 40, 60 to get to 600. So 63. I don't know, we can talk about multiplication and addition, how to think about them differently and make problems easier for yourself, but you need 3 ways of doing it. That'll cover it. Subtraction. Probably a good idea. Let me check my email real quick. Make sure I'm not like blocking people out of the stream or something. That looks good to go. All right, so for number 2, it says an explanation of the first 2 problems here, and again, I don't have the picture for them, and talk about segment addition postulates. So the 3 problems that we had way at the beginning of the school year, where basically these, I might be memorizing or remembering them a little bit differently, but basically we had a rectangle like this, and it was broken up into little pieces like this. I guess this one is a square technically. And then we had another rectangle, very similar problem. Except all it did was break things down like this. And this was definitely a rectangle not drawn to scale. And then there were some parts that were highlighted. So like this part right here, from here to here, they said was something like 7 centimeters. And they also said that this part, I think it was here. They said it was something like 18 centimeters. And then we had another problem that was slightly different. Looked like this. It had no tick marks at all on it. And it said this much was 13 centimeters. And they wanted you to find the perimeter of each of these. So, taking a look at the first one, segment addition postulate tells us that as long as we have a bunch of segments that are all the same length, it doesn't matter which way I arrange them. Right? I've got 3 segments there, and if I rearrange it to look like this, as long as the lengths haven't changed between here and here, then the total length of this piece is going to be the same. It doesn't matter how I bend it. And this seems kind of obvious, right? But that's why it's a postulate, right? It's not something we can prove. It's something that it just has to be, and if it wasn't, then it would screw up all of math. And so we kind of take a leap of faith on it. So this thing right here is 7 centimeters. And using that logic, since all these pieces are equal, if I've got 3 and then 1 here, I can go 3 and 1 here and say that's also 7 without having to do too much, right? I don't have to divide like 7 by 4 to figure out what each individual one is. And then if I know that 4 pieces is going to get me 7, I can also logic that 2 pieces is going to get me half of 7, which of course is 3.5. And there's 3.5 here. And even if you didn't know 3.5 was half of 7, you could say 1, 2, 3, 4 pieces, right? Even if they're apart, I can stick them together, and that's going to be 7. So we've got 7 times 3 means this is going to be 21 centimeters altogether for the perimeter. Here a little bit more difficult because not all the sides are labeled. But by segment addition postulate, we know that if sides line up perfectly, whatever this length is here, which we don't know because the whole thing's 18. I don't know how much this is. This amount will be the same here and here. So in other words, I can say, look, here's this whole length, which is going to be 3 pieces long. I know that because it's lined up. And then I've got 1 length here. So this is also going to be 18. And once again, half of 4 is 2. So half of 18 will be what this is, 9. So we've got 36 and 9, which is 45. And I'm pretty sure I remember these incorrectly, but it's basically the general idea for what's going on. This one's the weird one that everybody got tripped up on. And it's going to combine both of these ideas. The idea that we can rearrange stuff, and it'll still be the same length. And the idea where, hey, if this matches up, then it's going to be the same. So if we look here, a lot of people said when we were first working on this stuff, uh-oh. I think the string just dropped. I'm guessing stream dropped. Perkins. That sucks. All right, that was weird. Stream just dropped randomly. So a lot of people said when we first started looking at this, that if the shape didn't have this little indent, we would know that this is also 13 centimeters. And the reason for that is just this piece right here from here to here clearly matches up with this piece from here to here. And so whatever this length is will be the same as that. So this length is the same as that length. And then we also know that from here to here and here to here, right, is going to be the same. And so this length, whatever it is going to be the same as that. And so if these 2 pieces match up to these 2 pieces, then the whole thing will match up, right? We've got part 1 plus part 2 should equal part 1 plus part 2. There's some segment addition postulate there. But of course, that's not like the actual perimeter of the shape, right? It's got this little bend in there. So what do we do with that? Well, this little piece here, we'll call it the yellow piece. And this little piece here, we'll call it the blue piece. When you map them out and like the actual like length that we go around this little piece right here, yellow, blue, and then this little piece right here to kind of fill out the whole side. And if you notice, yellow is directly across from this little piece, which means that this piece right here is the same as that piece. And this blue piece is directly across from this. It means they're equal. So if you follow the path that we take from dot to dot, either the path like the kind of like L shape right here that we made, or the actual path of shape, here's what you do. You go through this much of the green piece, and then you go through a blue piece, a yellow piece, and then this much of the green piece. That's the outside. If you go through the regular path, you go through, again, this much of the green piece, a yellow piece, like we did before, a blue piece, and then you go through this much of a green piece again. So we've got this segment right here, which I could call like A, B. Let's do this. Let's do A, B, C, D, E, and we'll call this F. So it looks like one way around, we've got AB plus BC. This is the actual shape, plus CD plus DE. And the other way around, we've got AB down to here plus BF plus df plus de. And what's interesting about this is that, again, BC and DF are both yellow. They're both the same piece, right? And we know also that CD and BF are the same piece. And of course, AB is the same to itself and DE is the same to itself. So if you look, this is the exact same thing. These two bits are equal, which means that if this around through here, the long way, is 13 centimeters, it turns out it's not even that long. It's going to be the exact same length as this little piece, right? This bit right here where we go inside. So the length around this way will be the same as the length around the actual shape, which means this is 13, that's 13, total 26 centimeters. And I'm sure I got that one right and memorize it from the, or have this problem memorized from the actual assignment that I gave you guys. So that's the big brain play there, right? It's noticing that these things line up, and so they're going to be equal. These things line up, so they're going to be equal, and so they're switch outable, right? We know that if they're both going to be yellow and they're both going to be blue, green plus yellow and blue is going to be the same as green plus yellow and blue. So if this is 13, this path is 13. That's the first two. Then we're supposed to prove vertical angles theorem. Get this out of the way. And of course, vertical angles theorem is also known as scissor theorem, right? Your words, not mine. And when two angles scissor each other, they are the same by definition. So here's two angles that are created, well, really four, that are created by this x. And so what vertical angles theorem says, it says basically whenever you have an x, the top and bottom angles and the left and right angles are always going to be equal, no matter what x you make. And that makes sense, right? If I have a pair of scissors like this, why is the screen not working? All right, back again, I guess. I don't know if Twitch is being weird or if it's on my end. But basically, if you have a pair of scissors, right? No matter how far you open them up or how far you close them, the angle, as long as you keep the center point the same where they intersect, the angle in top and bottom will always be equal. So right now, they're very large angles that are equal, and right now, they're very small angles that are equal. And so this theorem explains that and why that is. And we're going to be using that a lot. So our job is to prove, essentially, that this top angle, this blue angle, is going to be congruent to this green angle right here. This bottom angle. Now, we can't just go with this much information and get that done, because that's going to be the actual theorem. It's dropping again. Hopefully it's still recording. So we can't just say that these two are going to be congruent, right? There's not enough information to pull that off. If that was the case, it wouldn't be a theorem, it'd be a postulate. So we need some more information to be able to prove that these two are congruent. Right now, all we know is about these two angles. So I'm going to bring another angle into the fold. I'm going to bring this pink angle in. And it's going to be the bridge that kind of brings green to blue. So linear pair theorem says that if I have two angles back to back on a line, then I know they're going to be 180 because that's how much a line is, right? This is a straight line, and so this is going to be 180 altogether. Sorry for people watching live, we just snapped back in. So I know that these two angles are going to be 180 altogether. That's linear pair theorem, linear meaning line, pair meaning two. So I know the measure of the blue angle, whatever it is, and the measure of our pink angle, our side angle, adds that up to 180 because, again, this is a straight line. And the thing that allows us to say that is linear pair theorem. So by LPT, I know that. Well, I also know that pink and green are going to be 180 for the same reason, right? Also by LPT, I know pink and green are going to add up to 180 because they're a straight line. So all that by linear pair theorem. And then through some algebra, since I know that this equals 180 and that equals 180, I can set those equal. And I'll show you what I mean by that. Kind of strange, and we don't make you guys think about this a lot when we're working with regular numbers, which is why when we switch out the regular numbers with variables, you guys lose your freaking minds. But if I know that 3 plus 4 equals 7, and I also know that 5 plus 2 equals 7, then through this logic, since they both equal 7, it makes sense to say that 3 plus 4 also equals 5 plus 2, right? If these two bits right here, this bit and this bit, both equal 7, then I can say that those two bits equal each other. Call that substitution. And so I know that this equals 180 and that equals 180. Therefore, little therefore symbol, the green plus the pink is going to equal the blue plus the pink. Let me scoot that over a little bit. And then, since I know this now, right, if these are both going to equal each other, then I can prove that blue and green are the exact same number, right? I've got something plus pink equals this something else plus pink, right? Well, if you take a number and you add a certain amount to it, right? Some number is pink and you add a certain amount to it. And that is the same amount total that you get after you take the first number and add another amount to it, right? You know these two amounts are the same. And that's probably easier to show with algebra than it is to say with words. So what I'm going to do is I'm going to subtract the same thing from both sides. So I'm going to subtract the pink angle from this side. I don't normally show my algebra like this, but I will show it today. And then I subtract from this side the pink angle. And since I did it to both sides, that's totally fine. This is subtraction property of equality. If I have an equality, I can subtract something from both sides, and it's totally fine. And when I do this, what happens is this goes away. Pink minus pink is nothing. So all I'm left with is the green angle on the left. And on the right side of the equal sign, all I'm left with is the blue angle, which tells us that the measure of the green is going to be the same as the measure of the blue. In other words, that these two angles are congruent. So this proves that these two angles are the same angle. And you can do the same thing with the side angles as well. So that's vertical angles theorem, right? That any x you have, the top and bottom will be the same. And the reason for that essentially is because this is a straight line and that's a straight line. When two straight lines cross, the top and bottom will be the same because straight lines produce 180s. And if they're both 180, then they equal each other. And if you subtract what's common, right, what's left over is going to be equal. So that's 3. 4, we're explaining parallel postulate. So this is another postulate, meaning we cannot prove it, which is why we're going to explain it. And parallel postulate is like this thing that Euclid for a long time with his 4 postulates in geometry, the 4 leaps of faith that he took to like connect all math together. He was very hesitant to add this 5th one. He thought he could prove it. He thought it would be a theorem. And after a long time of trying to prove it, he failed to, and eventually just said, okay, look, it has to be this. I can explain why it should be that. I just can't prove that it is. And here's what he said. He said, if you have a transversal, which is this line that cuts 2 other lines, okay? 2 of any line. Doesn't have to be parallel. As long as this line cuts 2 lines, we call that line a transversal, right? And he said, if the lines are parallel, then we know that this angle and this angle are going to be supplementary. So that's parallel postulate. It says that if the lines are parallel, then the same side, right, because they're on the same side of the transversal, I could have done these as well. The same side interior, inside the parallels, same side interior will be supplementary, which means, in other words, parallel postulate says this. If all these lines L and M, L is parallel to M, then the same side interior angles are supplementary. And of course, in this example right here, are supplementary. And in this example right here, what it would mean is that the measure of the green and the measure of the pink add up to 180, right? That's what supplementary means. So that's explaining it, what parallel postulate is. Now we're going to use it to solve some problems, right? So I give you guys a diagram. And we're supposed to figure out what angles are congruent to what. So here's what the diagram looks like. Very basic transversal diagram. So I've got something like this going on. And I tell you that these two lines are parallel. That's what those symbols mean. And so your job is to figure out what angles go with what. So let's just color an angle so we can start talking about it. So here's a green angle. And so I know by vertical angles theorem, right, which is what we talked about last time, that whenever I have an x, two straight lines crossing, right, then the opposite angles are going to be congruent. So top and bottom here are going to be congruent. I also know that this angle right here is going to be congruent to this one right here by vertical angles as well. Now, what do I know about this? Well, same thing, right? I can get these two together and these two together, but it turns out these angles are actually going to be related to these as well. We know by parallel postulate, right, that this angle right here, whatever it is, let's do it in black because we don't know what it is yet. This angle right here is going to be supplementary to this one, right? Parallel postulate says if the lines are parallel, then the same side interior angles are going to be supplementary. So I know that the measure of the black angle plus the measure of the green angle is going to be 180. So I'm going to write that down. And I know that by parallel postulate. There we go. I'm a little more zoomed in than usual. I got to get back used to showing this. So if I know those two are going to be supplementary, right, by parallel postulate, and I also know that these two are supplementary right here, and I know that by linear pair, right, because we have a straight line, two angles back to back. So I'm going to write that. I know those two are supplementary. I know the green angle and the blue angle add up to 180 by linear pair theorem. And if I know that, well, same thing as before, right? I know this equals 180, that equals 180. We know we can substitute those, and we can rewrite this as the unknown angle plus the green angle is going to equal the blue angle plus the green angle. And then by a subtraction property of equality, I can subtract both of these from the same side, right? And I end up with this. The black angle is the blue angle. Again, the idea is that green and blue make 180, and green and something else makes 180. Well, that something else also has to be blue, right? Then I can use vertical angles to get this to be blue. I can use the same logic that I used here for these two angles, right? By parallel postulate, this angle and the blue angle must be supplementary. And I also know by linear pair that blue and green is supplementary. So blue and something, blue and green are both 180. Well, that something's going to be green. That was by parallel postulate in combination with linear pair. Same thing down here that I did before, just with different angles. And then finally, I can use vertical angles theorem to get that last one. So that explains what angles are congruent whenever you have a transversal crossing two parallels. You're going to need three things to do it. We've used vertical angles to get cross angles, right, like this, congruent. And then we also had to use parallel postulate, which was the thing that allowed us to connect across here, right, this supplementary connection right here. And linear pair, which allowed us to get 180 for straight lines. So those three things together are going to get you all these different angles and kind of help you along your way. This is a pretty basic problem and a pretty common problem. They'll like obscure it somehow by like turning it, being like, okay, same problem, figure out the angles, all that. But probably the hardest thing to do is what I asked you guys next to do, which is number 5. And it was a diagram that looked something like this. And again, I don't have this diagram memorized, but it was something like this. It was, again, we had some parallel lines. Draw them nice and big. And we had some other parallel lines. And then we had another set of parallel lines that did something like this, I think. And the question was, what angles are congruent here? So we have a couple intersection points that we need to look at and figure out what angles go with what. And this was kind of a tough one. And part of the issue is that there's lots of extra lines. Here, the problem wasn't too bad because we had 2 parallels and 1 transversal. Here, we have 2 parallels, and then we have a transversal here that goes across them, and a transversal there that goes across them. Right? So there's lots of different things to look at. And if you want to just isolate one at a time, this problem becomes much, much easier. So what I like to do for problems like this, I do this in my head usually, but if you're new at this, it might be better to trace over like I'm doing, is I'm going to pick 2 parallel lines from before, and I'm going to pick 1 transversal to focus on. So this is a transversal. That was one of my triple parallel lines. And so I'm just going to focus on these intersections right here. Well, I know from before that these will be the same because of vertical, and these will be the same because of vertical. I know this will be supplementary, and since these are supplementary, I know this is green. And then by vertical, I know that. I know that these are supplementary by linear pair, and I know these are supplementary by parallel postulate. So green and blue go together, so this is going to be green and blue here, and then vertical angles. Now I can apply that to my regular diagram. I'm just going to stick it right here. That means this angle is going to be blue, and this one's going to be blue. Again, directly across from each other, you can imagine that X, ignore this line. And then we had this going on here as well. Now you'll notice these guys right here, this line is not present on our diagram. So I'm just going to ignore that line. This entire angle is green. Same thing here. These two put together. Just ignore that line for now. So these 2 angles put together are a green angle, the same angle as that angle there. Now I'm going to pick another set of angles to look at. Let's take a look at the one over here. So same 2 parallel lines. Now I'm going to add this transversal in. So now I'm ignoring this. You'll notice that, actually, let's ignore this line for now. So if I turn this, it might be easier to see it. So you'll notice we had a similar problem as before, right? We have a linear pair right here, so these are supplementary, right? Green and blue. Well, I also know blue and this should be supplementary because these 2 are parallel. So this should be a green angle. And then by vertical angles, we get this. Here we've got green, and it should be supplementary with this angle, right? Well, I already know green and blue are supplementary, so guess what? That's blue by vertical. Then I can look, same thing here, right? I know these 2 will be supplementary. Well, I already know green and blue are supplementary, right? These 2 are parallel. So if that's blue, this is going to be green. And then by vertical angles, this. And then same nonsense, right? By parallel postulate, I know these 2 are supplementary, and I know by linear pair, these 2 are supplementary, so green and blue go together. So if that's green, this one's blue. And now I can apply that to my main diagram again. So I'll slide this down. Maybe over. We'll slide it over. Yeah, it'll work. So we're looking at this line right here and these 2 lines. So it looks like this is going to be blue and that's going to be blue. Makes sense. It's vertical angles right there. We have 2 lines making an X, right? And then I also have these 2 that are going to be blue. And these 2 will be green. And this whole thing, once again, this line isn't present, so I just ignore it. These whole things are going to be green. All right, so if we look in this corner right here, you might be tempted to say these are blue and green as well. But notice that blue and green here came from these 2 parallels in this transversal. Then we got blue and green again by looking at the same 2 parallels and a transversal that was parallel to the first one, right? So these are essentially the same line. So whatever happens here is going to happen here, and that's what we found. Here, because this line isn't parallel to these other guys, right? It only has 2 little marks there. It's going to have different colors. So what I'm going to use is orange for this angle, and then I'll get vertical angles there. And let's highlight a little bit. Let's do the other as purple here and here. And then let's break this down. So let me get another piece of paper and trace over. isolate some things. I'm only going to focus on these two parallel lines again, but with this transversal. There we go. So there's our single parallels, and there's our double. So we already said this was going to be orange, and this is purple. And then from here, I think it's pretty easy to figure out what's going to happen down here, right? Orange and purple are supplementary, so orange and purple should be supplementary, and then we get vertical angles there. Again, orange and purple are supplementary, so purple and orange will be supplementary here. And if we scoot this over, we can see that this purple angle right here is just this much of the green angle. Right there. And then across from that, directly across, was the vertical angle. So again, this much of the green. And then this orange angle is actually going to be part of the blue and part of the green, right? This line doesn't exist on this one. So orange is this amount. And then directly across from that, again, part of the blue, part of the green, is orange. So now what I'm going to do is I'm going to look at these two parallel lines once again, and then instead of focusing on this transversal, I'll focus on this one, this other double, right? And they should be treated the exact same way. So if you're clever, we don't even have to draw this again on here, but if you want to, you can. I'm going to notice that, look, part of blue and part of green is this orange. So if I just slide this over, part of blue and part of green will be orange. Part of blue and part of green here will be orange. And then just this much of the green should be purple. And then by vertical there. All right, so I've used the doubles as transversals, and I've used the triples as transversals for this. So what I'm missing now are spots like this guy here and that guy there. These two spots, that's all I'm missing. So if you look at this intersection, it's made up of this parallel and or this line right here, and then this line right here. So a couple ways to look at this. One, if I look at this paired up with this and have this be the transversal. So if I look at it like this, here's the intersection we want to talk about. If I, once again, take these two and look at this guy, this right here is going to be similar to this one right there, right? We have two lines that are parallel, and we're using this as the transversal. So these two are going to be the same. So I can see that that's orange, then this will be orange. And if that's purple, then this will be purple. Again, the idea orange and purple are going to be supplementary. Ignore everything else except for these two. Orange and purple are supplementary. So these are orange and purple. And if this is purple, then I know this is orange. Makes sense, vertical angles there. And then vertical angles here for another purple. So I've knocked everything out except for, I think, this one, which is just an intersection of these two lines here. This is kind of weird, right? We only have two lines going into this intersection. One's a 2 and one's a 3. So what are the angles going to be like? What kind of angles are going to show up here? Well, we know from looking at our diagram that it looks like there's also some angles here that are missing, right? Top and bottom that aren't showing up. And whatever this angle is, it adds with blue and purple to make 180. Well, you'll notice that this is kind of a triangle up here, right? It's a triangle. Blue and purple plus whatever this has to add to 180 as well, because triangles always add to 180, the internal angles. So blue and purple plus whatever this is 180. Blue and purple plus whatever this is 180. Well, those angles must be the same. We also know down here, blue and purple, whatever this is going to add up to 180 because it's a straight line, right? And by vertical angles, we know this is yellow. So a couple different ways. Here, blue and purple and something makes 180, so I'll call this yellow. Blue and purple, something here makes 180, so I'll call this yellow as well. And then lastly, we have this angle, which is going to be yellow by vertical angles. I guess not lastly, because You notice there's also some angles here on the side. So yellow and what's going to make 180? That's what's going to happen here, right? Something in yellow has to make 180 because that's a straight line. So I guess it's going to be purple and blue put together. Well, purple and blue put together, we don't really have anything for, right? Purple and blue put together is a little bit of green, a little bit of orange. So we need another color. So let's do pink. And that'll be what purple and blue put together is. Making up this angle here. So if you wanted to, this is technically pink because it's purple and blue together, and this is technically pink because it's purple and blue together. Same thing here, here. And it goes with yellow to make 180, as you can see. Pink and yellow. And that'll cover pretty much everything. So yeah, this one's pretty nuts. But if you break it down piece by piece, it's not too bad to get started, and then you can start noticing patterns. Once you've developed a basic framework for, hey, I know all these are equal, right? And I can go through and show it with linear pair theorem / parallel postulate / vertical angles, then the rest kind of falls into place. Right? Once you get like these two set up, then you can start going through and matching up other things. And again, for me, I'm not worried about you getting all of these. It's just showing that you can do most of them and understand where these connections are. Like if you didn't see that this is also pink down here, because hey, pink is the same thing as blue and purple put together for some reason, right? That's totally fine. I don't need exact specificity on all this. I just need to see that you're able to make these connections in different ways. So I should see at least one pair of angles, two pair of angles, three pair of angles showing up here in this situation. That makes sense because we're going to have three different pairs of angles because we've got three different pairs of parallel lines. So that's one of the harder ones we do at the beginning of the year. If you want more help with that, I can help you guys with that at some other point. Let me know, especially if you have questions as you're doing it. That would be very helpful. All right, so that's 5. 6 is talking about Super Mario Twins. So when we did this, what had happened was there was a Mario Desmos activity, and the first level or so talked about just setting the slope using points. So like they had a bunch of coins on a coordinate plane. Something like that. And you had to make Mario fly through them. And so the way you did this is you set up the line that he was going to fly on by, for the first level at least, telling where to put 2 dots to make the line, right? Because any 2 points will make a line, right? And you tell where to put the dots. So these are the coins. We need to tell where to put dots. And if you know anything about lines, you know that if these coins are all on a line, which appears they are, if I just put my dots on, 2 of these coins, maybe, here and here, then that will guarantee that Mario will fly through all of them. So what you had to do for the first one is talk about that, and then maybe it was like 2, 3, you wanted your first dot on, and this one looks like it's 6, 9. The other one. Pretty boring first level. Right, pick your dots where to put them. You can even put them in between the coins if you want. As long as it's on that line right there, you'll end up hitting them. And then the second level talks about using slope and the y-intercept to hit these coins. So, speaking of slope, the idea is that slope is going to be, that's an equal sign, looks really gross, but it's an equal sign, is going to be the vertical change, or vertical distance, I suppose, that you travel on a line over the horizontal distance you travel. So it's a relationship, because we're using division, between these two concepts. So if my line, coordinate plane, is traveling like this, do that. Here's my line. And you'll notice that every time I go 1 to the right, I go 3 up, right? We talk about rise over run, going up 3 over 1, and that's going to be our slope here. I'm going 3 vertically for every 1 horizontal, or 6 vertically for every 2 horizontal. And again, these slopes are going to be the same, right? The relationship between 6 and 2 is the same relationship that 3 has to 1, right? 3 times bigger. So to map out your slope, if you want it going up, right, we're going to go up 3, so positive number, and then over 1 to the right, so another positive number. If you wanted your slope to go downward, right, a line to go down, then we need one of those values to be negative, right? We can go down 3 and still to the right one, and that'll get us our slope. Or we can go up 3, this is going to be kind of weird, up 3 and to the left 1. So if I go from here to here, let's pick a point here, I suppose. I didn't draw this line very well. Let's do this. There we go, here's our line. So if I go up 3 from this point and over 1 to the left, and again, left means negative, then I also get the exact same line that I was talking about earlier. So either way, these are going to be equivalent, right? This slope and this slope. And so we're going to use that to figure out where to get the coins. So as I'm using the points here to figure out what my slope might be, you can use the coins to figure out what your slope might be as well. So for this last example, right, we can find the line by just putting the line through these two dots. That's fine, but we can also give the equation of this line by saying its slope and y-intercept. So the slope here looks like we're heading up between these points, right, from here to here, 3, and we're heading to the right, 2. So our slope is going to be 3 over 2. Vertical over horizontal. And then for the y-intercept, that's going to be where it hits the y-axis, which of course is this line. And it looks like my line, if I were to draw it correctly, hits the y-axis at 0. So our y-intercept would then be 0. And that's all you have to do for the first one. You have to set your y-intercept accordingly, right? And that y-intercept is going to raise the line up or down, right? If I started here on the y-axis instead, this is a y-intercept of 1, 2, 3, 4, 5, 6, 7 instead of 0. And then I applied this slope, up 3 over 2, up 3 over 2. It would be the exact same line, just scooted up 7. So setting the height of your line is going to come from the y-intercept. And then the angle at which you're going to attack those coins is going to come from your slope. Again, if you wanted it going downward, you make one of these negative. So you go down 3, right 2. And that's how you make your plan of attack. And so describing that is what I want to see in the portfolio, is what you did, what your plan was, and then also how you adjusted the slope to make it work. So for some of these things, it's kind of hard to tell where the coins are on the graph. And so for that, what I would do is if your line is, let's say here, but the coin is just slightly above that, right? It's like right there. And you're just missing these coins just by a little bit. What I would do is I would say, look, I know I need that line steeper, so I need more verticalness to it. So I would increase this top number, maybe make it like 5 over 2 or something, and see if that hit the coin. So being able to move that slope back and forth and adjust it to what you need is a skill that I want you guys to be able to have. So if I wanted the opposite of that, let's say the coins were actually below this line. Oh, my thing's freaking out. There we go. So if it was below this line, like my points were like here, then I know that I need to increase this bottom number, or vice versa, decrease the top number, right? Make it less vertical or make it more horizontal in order to hit these because the line's flatter. We've talked about how in class that the flattest slope is 0, right? A line like this that has absolutely no slope to it. And the steepest slope is undefined, a line like this. And the reason for that is that when we go here, we're going up nothing, so 0 for the verticalness. And for this one, we can go to the right as much as you want, right? Go up 0 over 1, and we go from there to there. That explains the slope. We could also go up 0 over 2 and get us to there. Doesn't matter what the number is down here. 0 divided by anything is 0, so our slope is just simplified to 0. Whereas here, it's the exact opposite effect, right? We're going up as much as you want, so maybe starting here, going up 3. And then we're going over nothing. Now, 0 divided by anything is 0, but anything divided by 0, the opposite of that when these are flipped, is undefined. It doesn't give us a proper answer. And if we had this be defined to be any number, right, we can define this as 0. If we define this as 0, it would end up breaking math. If we define this as 1, if we define it as anything, it would end up breaking math. So we call it undefined. And let me show you how it breaks math. If I say 3 over 0 equals 0, which is what a lot of people like to say, then I should be able to cancel this divide by 0 by multiplying by 0. And when I do that to both sides, which is totally legal, I end up with this. 0 and divide by 0 cancel, and I get 3. And 0 times 0 is 0. And obviously, this is a false statement. So I did everything fine, and it led me to a bad conclusion, which means I know that this cannot be true, that 3 over 0 can't be 0. A lot of people say, well, what if 3 over 0 is 1? Well, the same nonsense happens. If I treat it like any other math problem, I should be able to cancel the divide by 0, and I get 3 equals 0, which again is a false statement. 3 does not equal 0. So we can't define this as anything. We know it exists because it's a vertical line, but we can't give a number to it because if we were to, it would actually screw up mathematics. And math is not about obeying rules, but it's about finding things that are interesting and having stuff that can, 3 can equal 0, 4 can equal 0, anything can equal 0. While it makes math interesting for a couple seconds, it gets boring pretty quickly when literally anything can be 0. It's almost like the kid in 3rd grade that's like, okay, what if we were all floating on the ceiling? It's like, well, okay, what if? After a while, that gets pretty boring. Rules suck, and I'm not a big fan of them, but they give you a box with which to create in. And so when you break those rules or you operate with inside them, it gives a meaning to what you're doing. And if we just have everything equaling everything, math is pretty pointless. More pointless than it already is, right? So there's slope. Horizontal slope of 0. Vertical slope is undefined, right? We can adjust our slope back and forth by increasing the top number to make it steeper or increasing the bottom number to make it more horizontal. And then our y-intercept sets where the line's going to be at on the y-axis, starting from here, starting from there, starting from, down here, wherever. And so that's Super Mario Brothers in a nutshell. Next, we've got Pythagorean theorem and what it means, and prove it using any proof you like. So the proof that I like for Pythagorean theorem is this one, and I would highly encourage you to do it as well. I think it's pretty easy to follow, or at least easier than some. Pythagorean theorem states that in a right triangle, so here's a right triangle, this side's length, we'll call that A, some side length there, and this has some side length here, and this has some side length here, that if you were to square this side, so taking this and squaring it, and you were to take this length and square it, you would get the hypotenuse length squared. So in other words, a squared plus b squared equals c squared in a right triangle. The two smaller sides, when you square and add them up, you get the third side squared. So what does this mean? First of all, when we say squared, we literally mean squared. What we mean is taking this side right here and making a square out of it. So if this is length A, all these sides are going to have to be length A to be a square, right? And so what you get is the area of the square is base times height, which is A squared for the whole thing. So we have a square of A in length, and then we also have a square, and I won't be able to draw it on here because I drew it too close to the edge. A square of B in length, B squared. This goes out further. And if I were to take these two squares, let me draw that a little thicker. If I were to take these two squares, and again, it goes out further, and I were to add those two squares together, their areas, what I would get is the area of this very large square. A square of C, base times height being C squared. And it's kind of cool that you can take the squares of these sides and add them up. The sides will not add up to C. A plus B does not equal C. That's not what they're saying. They're saying the squares here will add up to this guy's area. It's kind of convoluted, but it's a true statement. How do we know that this is true? That's what we're going to be proving right now. How do we know that A squared plus B squared is always going to equal C squared in the right triangle? And there are lots of different proofs for this, but the one that I think is easy enough for beginning geometry students to figure out is this one. So imagine you have that ABC right triangle, right? And we're going to prove that for any three sides of a right triangle, A, B, and C will relate by Pythagorean theorem, right? A squared, B squared, when you add them up, will equal C squared. So here's our triangle, right? We're going to prove that when you square this, square that, and you add them up, you get this guy squared. So one of the proofs is this. Let's make 3 copies of this triangle. And what's going to happen is that each of these triangles is going to be a slightly different copy than the last. The first one is going to be the smallest, and that's because we're going to take the smallest side and we're going to multiply it by itself. So all the sides are getting multiplied by A. So this is times A, and what we get is A times A, which is A squared. Then we get A times B, which is, of course, AB, right? Whatever those two numbers are times each other. There's a little dot in between there if you want to imagine that. And then we have A times C, which is just AC. And that's the length of this side now. If we apply that same thing here, what we're going to do is we're going to, instead of multiply everything by a, we're going to multiply everything by b. And so b times b is going to get us b squared. And a times b is going to get us ab. And b times c is going to get bc. Lastly, following this pattern, we're going to multiply everything by c. And what's going to happen is this side is going to become c squared, because anything times itself is the square. And a times c is going to be ac. And b times c is going to be bc. Now, I said we're going to make 3 copies of this triangle, but obviously these are different triangles, right? They have different side lengths. So what do I mean by copies? What I mean is that these are all going to be the same triangle as this, except bigger. Well, what does that mean? It means that the angles are all going to maintain the same. So if it was a right triangle before, it's still going to be a right triangle after we're done. Well, what about this angle here? How do I know that this angle is the same as that angle still after I multiplied? Well, the reason I know that is because I can think of this angle, instead of measuring it with like a protractor or something crazy, I can just think of slope. What's the rise over run from this point to this point? Well, if I rise by b and I run by a, that's going to be the slope of this angle right here. This angle's slope is going to equal the rise, b, over the run, a. And if the slope is the same for this angle here, then they're both going to be the same measure. So if I look, the rise here is AB. So this angle is going to have AB for its rise. And the run is a squared, right? We're running a squared and we're going up AB for this angle here. And of course, a squared is just a times a, so I'm going to write it like that just so it's easier to show what's going to happen next. This is all multiplication and division, so we can do it in any order we want. This is a divided by a. Anything divided by itself is 1. And 1 times b over a. 1 times anything is itself, so 1 times b over a is just b over a. And so after doing a little bit of calculation, we can see that this slope is b over a for this angle, and this slope is also b over a, which means these two angles are in fact the same. If I apply that down here for rise over run, you'll notice that the rise is b squared, so b times b, and the run is ab. Once again, anything divided by itself is 1, so b divided by b is 1. 1 times anything is itself, so b over a is what we get here as well. So once again, multiplying everything by b also preserved this angle, so it's blue. And if you look down here, BC over AC is what we're going to get, rise over run. The C's are going to divide out and make 1. And 1 times B over A is what we'll get, which is just B over A. So this will also be blue angle. Now, for the last angles, there's a couple ways you know they're all the same. One way is that, look, I know all these have to add up to 180. So blue plus 90 plus whatever this is 180. Blue plus 90 plus whatever that is 180. Well, these guys have to be the same for that to be true. But another way you can do it is you can do the same thing we did before. And it might help if you turn the diagram. A's and B's look so much the same when they're sideways, so it's kind of hard to tell, but that's why I color-coded them. So if you look here, the rise of a run here is the rise is A, the run is B. So A over B this time. Here, it's A squared over AB. A's are going to cancel, we get A over B. So these angles are the same. Here, you're also going to get A over B, because 1B each is going to cancel, you're going to get A over 1B. Here, the C's are going to cancel, and you're going to get A over B. And so these are, in fact, all the same triangle, just bigger, right? This one's multiplied by A, that one's multiplied by B, and that one's multiplied by C. So what? What does this do for us? Well, the guy that made this proof realized that if we take these 3 triangles, we get this shape right here. We can put them all together like this. There's our 3 right triangles. And you'll notice that this sort of looks like a rectangle. And what we're going to do is prove that it is. Now, a rectangle is made up of 4 sides, right? So we're going to have to prove that this fits perfectly together to create 4 sides. Obviously, that's a whole side. This is a whole side. And that's a whole side. But the question is this one side or is it 2 sides over here? Is there a little break right here where it bends, or does it go straight across? So our job is going to be to prove that this is a straight line. And the way to do that is to prove that this is 180 degrees. That's going to be our first job. Our second job is going to be to prove that all the angles are equal, right? All of them are 90. And if these angles up here are 90, here and here, then we have ourselves a rectangle. Now, why do we care whether this is a rectangle or not? Why do we care if these fit together perfectly to a rectangle? Well, if you label all the sides from all the triangles, right, this is the c-squared side because this is the biggest triangle, and we'll call this one the AC side because this is the hypotenuse of the smallest triangle, right, AC. And then the hypotenuse of the biggest, or the medium triangle is BC. That's AC, this is AB. If that's BC here, either this is B squared or AB, which is it going to be? Let's see. We turn it this way, it looks like it's going to be AB. And that's probably what we want anyway, right? We want these sides to be the same, because that's how a rectangle do, right? Opposite sides are going to be equal. And if you look, that means this is A squared here. And then this is going to be B squared. So if we can prove this is a rectangle, opposite sides are going to be congruent, right? If we can prove that this is a straight line and these are both 90, then opposite sides will be congruent. That means this whole side is A squared plus B squared. And it'll equal this side, C squared, which is what we want. So how do we prove that this is what it is? Well, if you look at the angles, AC and A squared, that's this angle right here is blue. That means the other angle must be pink. And for here, BC and AB makes the blue angle. So here's BC and AB. That makes the blue angle. This is blue. Means the other angle must be pink. And for the big triangle, C squared and AC make blue. C squared and AC is this angle, so this is blue. And the other must be pink. So how can I prove this is 180? Well, if you know about triangles, triangles always have their internal angles adding up to 180. So pink, blue, and 90 adds up to 180. Well, here's pink, blue, and 90. That means this angle right here must be 180. Which then this means this is a straight line. So we have a 4-sided shape. Are all 4 angles 90 though? Well, if you think about it, pink and blue and 90 add up to 180. So in other words, 90 plus pink plus blue plus 180. Well, if I subtract 90 from both sides, I get that the pink angle and the blue angle equals 180 minus 90, which is 90. And so I get that pink and blue must be 90. And that makes sense, right? 90 plus 90 is going to give us 180. So this has to be 90 altogether. I don't know what these are individually, right? It could be like 60 and 30 or 45 and 45 or like 89 and 1. I don't know. But I do know that together they add up to 90. Which means when I see these next to each other, blue and pink, I know that they're going to add up to 90. So this is actually a 90-degree angle altogether. And this is also going to be a 90-degree angle altogether. Pink and blue, once again, right next to each other. So if I know all 4 angles are 90, and I know I have 4 sides after showing this is 180, then I know it's a rectangle. Which means that A squared, this length right here, plus this length right here, B squared, is going to equal the top length, B squared. And there's our proof. Little swag box to finish it off. All right, so number 8 is saying, okay, now that we know that a squared plus b squared is equal c squared, how does that connect to distance formula? Because we've talked about that in class. Why are those two connected? Why is trying to measure the distance of a segment the same as taking the sides of a triangle, squaring them and adding them, and getting the square of the other side? Words are hard, math is easy. Let me show you what I'm talking about. So imagine you had a segment, and this segment was from here to here. And you want to know how long it was. Well, it would be really nice if we could just take the coordinates here, whatever they are. This guy is some value, and this guy is some value, right? Here and here is his coordinate. And then here are the coordinates for this guy. It'd be really nice if we could just take those coordinates, plug them into a formula, and figure out how long the distance is between these two dots, this guy here and this guy here. Measuring this is going to be difficult because it's kind of at an angle, right? So we just can't count diagonals here. It's kind of at a weird angle. So how do we solve a problem like Maria? Well, if you think about it, this guy's coordinates are just going to be some x, comma, some y. And this guy's coordinates are going to be some x and some y as well. Now, to keep things clear, obviously this x is bigger than that x. So I'm going to call this the first x and that's the second x. And this y is clearly bigger than that y because it's higher up. So I'm going to call it the second y and this one the first y. So what is the coordinates here? Well, it looks like it's x2, comma, y1. And this one is x1, comma, y2. So I'd like to be able to take these values, whatever they are in real life, and plug them into a formula and get the distance. So how is distance formula and Pythagorean theorem related? Well, it turns out that any segment that you want to measure can be turned into a right triangle. And you can do that simply by taking the distance between here and here, right? And the distance between here and here, and using that as the sides of the right triangle. Well, first of all, what is the distance between here and here? Well, if you've been in my class at all, you should remember that distance is subtraction, right? If this number were 10 and this number were 3, you would subtract them and say, oh, this distance between them is 7, right? The length here is 7. Well, since we don't have numbers, we can just use variables, and instead of saying 10 minus 3, we can say x2 minus x1. That will be the distance, right? If you subtract them, that's going to give you the distance of this red line, which will be exactly how long this red line is. Same thing over here. The distance is going to be y2 minus y1. That's how long this will be. And it should be the same distance as this segment from here to here. Clearly, this is a right angle because we have a perfectly vertical and perfectly horizontal line. They're going to meet at 90. And so now our question is no longer, how do I measure this segment? We can ask a separate question that's much easier to answer. What's the hypotenuse of this triangle? And we know that the hypotenuse will be whatever the sides are, squared and added together. And that'll give us this guy squared, the length we want to find out, right? So normally we'd write a squared plus b squared equals c squared. Well, a is just going to be however long this length is, right? So a is going to be the same thing as this. I know a is whatever happens when you subtract these guys, right? 10 minus 3 is going to get a 7, so a would be 7, right? It's whatever those guys are subtracted. And b is going to be whatever happens to the y's when you subtract them. Maybe this is 11 minus 2, and so it's 9 in length, and that's how long b would be. Well, normally we write a squared plus b squared equals c squared to figure out Pythag, right? Well, instead of writing a squared, I'm going to write what a equals. It's whatever this is squared. Plus whatever b is squared. And what that is going to get us is c squared, this length squared. Now, obviously, I don't care about c squared. I just want c, right? So in order to make this c squared turn into just c, so all this just equals c, what I'm going to do is I'm going to root both sides. When I root this side, I get a giant root over the top. It does not cancel these squares. And then over here, the square that was once there, I rooted and got rid of it, so they both cancel. And so now I have a formula that gives me the length, right? It gives me c. It's all this junk. It says take your x's and y's from here, right? Here's our x1. Here's our x2, right? Take those guys and subtract them. And take these guys and subtract them. So all I need to know is these 2 points, and I can plug it into this formula, and I'll get the length. So what we did is we showed that any segment can be turned into a right triangle, and that right triangle allows us to ask about Pythagorean theorem, which is a squared plus b squared equals c squared. A is just going to be the distance between these two values, and b is just going to be the distance between these two values. And so we have a formula built off of that. Applying that formula is pretty easy. You can pretend that maybe these points were originally, I don't know, let's go 2, comma, let's do 9, and then this point was, let's say it was actually at 11, comma 3 or something. And if you wanted to figure out the distance between these two values, what you could do is very simply find the distance between the x's, because that's what subtraction means, right? You can subtract the x values, this guy minus this guy, or just ask yourself, what's the distance between 2 and 11? 9. What's the distance between the y values, right? We're supposed to subtract them. 9 and 3, the distance is 6. And when I square that and root that, I'll get my length. 81, 36. This is going to be 80 plus 30 is 110, and then 7 out of the 1 and the 6. So 110 plus 7 is 117. Root 117 is going to be our answer. That's going to be a little bit more than 10, because root 100 is 10, right? Root 11 is 121, so it's going to be really close to 11. Just underneath, it's going to be some weird decimal. So there's applying it to some random points, right? We can quickly plug it into this formula, and we can avoid like actually plugging in the numbers for this if we think about what this means, right? This means subtraction, or subtraction means distance. So instead of actually plugging in 11 and 2 here and getting -9, I can just say, look, this just wants to know the distance. The distance is 9. The distance here is 6. Square them, add them, root them. So there's Pythagorean theorem, its connection to distance formula. It also asks you in the problem, what happens if I want to measure like a horizontal line or a vertical line? Well, you can imagine that if this line were vertical, what's really happening is like we're looking at a triangle that has no vertical value. What I mean by that is this. Imagine this B part right here shrinks and shrinks and shrinks, right? C's coming along with it. Here's C in purple, right? It shrinks and shrinks and shrinks and shrinks and shrinks until eventually C and A are one and the same. If you were to do Pythag with that, the distance here would have become 0, right? No verticalness. It shrunk all the way down. Then you would have had A, whatever it is. You would have squared both, added and root. 0 squared is 0, a squared is a squared. So we get that. And of course, the root of a squared is just a. So a and c are one and the same. Which makes sense. Again, c is this, and then as b shrinks to 0, c and a match up perfectly. You can also imagine the same thing if we had our line here and we were shrinking a. As a shrinks, c becomes b. Because then a will be the 0, and then we'll have b squared here, and when we root b squared, we get b equals c. So you can still do Pythagorean theorem even with a vertical line or a horizontal line. It's just as if we're looking at a triangle that's missing a side for a vertical line here or a horizontal line there. Now we're on to the back half. Transformations. 9 through 15 is all about that. And 9 is just asking what the general transformations are. So here's transformations. We know that there are 4 different transformations that we talked about in class. There's translation, which is to slide stuff. And we'll do that by vectors, right? Pushing things around, pushing one dot from here to here by a certain amount. And that'll be adding or subtracting for the x value and y value. So we'll take this, and then we will add or subtract a certain amount to move it around. So maybe this one is 1, 2, 3, 4 to the right and 3 up. So we'd add 4 to the x to go 4 to the right, and 3 to the y to go 3 up. We also have reflections that we talked about. I guess I'll write this in lowercase. And reflections are flips. And what that does is it takes a line of reflection, something like this, and a dot, something you want to flip, like these dots from before, and it will flip it directly across the line at a perpendicular angle. and equidistant on both sides. So the distance here from the mirror will be the same as this to the mirror. And that's how we'll reflect objects. What happens here for the flip or the reflection is complex, but an example of that would be like switching the x and the y across this line. That can produce a flip. One of the many rules. Rotations we talked about. And rotations are also known as turns. And what happens here is that we have a point that's used as a center for turning around. And then we have some object that we are going to turn around this. So you can imagine if I were to do a 90-degree clockwise or counterclockwise rotation, I might end up here. Let's do this and this. So my triangle would end up right here after 90 degrees clockwise rotation, or counterclockwise, I should say. And that's because you can imagine a little bit of a pinwheel. Some L's turning. And that's going to be a 90-degree rotation. In this case, it's clockwise. So an example of that would be taking your original coordinates and applying this rule. X and Y are going to switch spots. And that's because the horizontal part here becomes vertical after we're done, and the vertical part becomes horizontal, so they switch. And then we're heading to the left, so the first guy is going to get negated. Then we have, last but not least, dilations, which we learned about most recently. And those are shrink/grow. And what this does is it can grow or shrink your object. And so a rule here would say that we're doubling the x and doubling the y. What's going to happen is we're going to have some center that we are dilating from. Then we have some image like this. And not only is it going to make it twice as big in every direction, both the x and the y direction, but it's also going to push it twice as far away from C. So this point is 2 away from C originally, so now it's going to be 4. So it's going to end up moving to here. It's kind of funny, it maps onto itself. And then this one is 4 away, so it's going to be 1, 2, 3, 4, 8 away after we're done. This guy's 3 away to the right, so he's going to be 6 away. And then instead of 3 up, he's going to be 6 up. So our triangle kind of gets blown up along these lines. Twice as much in the x direction and twice as much in the y direction. Twice as wide and twice as tall. So not only does it get bigger or smaller, but it also can push further away if it gets bigger, or push closer if it gets smaller. That's what those look like. The first thing they want you to talk about in your next post, number 10, is what's, like, make your own translation, describe what's going on here. So what I would do is I would draw myself a figure, like a triangle. And then I would push it by some amount. So what we're going to use is those little arrows or vectors. This is not brackets like for a coordinate, but it's very similar. These are pointy brackets, which tells you we're dealing with a vector, which is an arrow. It's going to push things. So let's say I want to send this, I don't know, 5 to the right. Let's do more than 5 to the right. Let's do 9 to the right and send it 4 down. So this vector is what we're going to apply. 1, 2, 3. So we start on a point. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 4 down. 1, 2, 3, 4. And that point's going to end up here after we're done. And here's what the vector looks like that pushed from here to there. That's a 9, -4 vector. And if we apply that same vector to everything, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4. If we apply that to everything, 3, 4, 5, 6, 7, 8, 9, 2, 3, 4. Ooh, it's going to end up here. One, 2, 3, 4. Yep. Then what's going to happen is the entire object will end up moving 9 to the right and 4 over. And that's a translation of the slide. That's it. Nothing exciting there. The rule will be written like this. Take your original coordinates And of course, for this one, we're going to add 9 to the x, and we're going to subtract 4 to the y to move it right and down. Then we're supposed to talk about reflections, like basic ones. For our next post, this is post number, I believe, 11. And for reflections, there's really only 5 that you need to talk about. There's the basic reflection that happens when we reflect over the y-axis, the basic reflection that happens when we reflect over the x-axis, the reflection that happens when we move. We sort of reflect over the x or y-axis, but it's moved. You'll see that in a second. And then we have some reflections that happen when the line is a 45-degree angle line. So if we're reflecting over this line, otherwise known as the y-axis, if we're reflecting over this line, otherwise known as the x-axis, if we're reflecting over a line like this that is still vertical, like this one, but it's moved off the y-axis. And then what happens if we move or reflect something across this line? This 45-degree angle line going up. And of course, the opposite of that, the 45-degree angle line moving down. What happens here? So for this one, rule's pretty simple. If I have a point over here, that's -4, 3. What's going to happen is that reflections happen perpendicular to the line of reflection, so they happen straight across, meaning that our new point, A prime, is going to be somewhere on this line. And of course, it's going to be the same distance from here to here, which we can just count. So 4 squares, it looks like. So here's where A prime is going to be, and that new coordinate is 4, 3. So clearly you can see that the rule is take your original coordinates, and you're going to negate the x. So flipping across the y-axis is going to negate the x, and the reason for this is because what we're doing is we're flipping horizontally, so there's going to be horizontal change, right? That's what variable is going to change. We're going from the left side of the x-axis, right? Here's our x-axis. We're going the left side to the right side, so the sign is going to change, or right to left, whichever way. Here, same logic applies. Let's do the same point, -1, 2, 3, 4, 1, 2, 3. A. It's going to happen perpendicular to the axis of the line of reflection. So our new A is going to end up somewhere over here. And since it's 3 away from the line, it's going to be 3 away when we're done. And if you look at the coordinates, it's -4, it's -4, 3 is going to end up being -4, -3. So you can see the rule is take your x and y. The x stays the same, they're both -4, and the y changes sign, so it gets negated. Here it's going to be the same idea as this one, right? We're going to negate the x value because we're flipping left to right. We're flipping horizontally. 1, 2, 3, 4, 1, 2, 3. But because the line has moved over, what we've done is we've translated that line 3 to the right. And so our rule is going to look a little bit different. Instead of just simply negating something, what's going to happen is we're going to move 3 to the right, which is going to add 3 to our x value. That translates everything over, just like we were doing earlier with this, right? We wanted to move 9 to the right, so we added 9 to the x, right? Here we're just moving 3 to the right. And then we're also going to add 3 again, because now, if you look, the distance between A and the normal line of reflection, right? It used to be 4, but now it's 7. We've increased that distance by 3. And so now that this has increased, A prime, the new reflected point, is also going to have to increase by 3. So we're going to add whatever this number is twice, essentially. And then, of course, negate it because we're going to be flipping horizontally. There's our rule. If you want to simplify it, you can write it like this. There's our rule for this. And then over here, for these two lines, what's going to happen is if you reflect 1, 4, 1, 2, 3, this line point right here. Since it needs to be perpendicular to this line, this slope is a 1/1 slope going up and to the right. We want the negative version of that going down 1/1. And that will make sure we hit everything at a 90-degree angle. And same distance across is here. 1 diagonal, 2 diagonals, 3 diagonals, and a half. So half, 1, 2, 3. And you can see our rule is now this. What we've done is we've taken x and y, and it looks like what we've done is we flipped them both. X and y have switched spots. And that's because the horizontal part here was 4, and now the vertical part here is 4. And the vertical part here is 3, and now the horizontal part here is 3. So x and y switch spots. The same thing's going to happen down here. 1, 2, 3, 4, 1, 2, 3. Okay, as we flip it across, it's going to be perpendicular. There we go. Same distance on both sides, so A prime is going to be here. And you'll notice that the pattern is now we have -3, +4. So not only did x and y switch spots, but they also changed their signs. So they switched, and -4 became a +4, so it got its sign changed. And 3 became a -3, so it got its sign changed as well. So there's our 5 basic reflections. Negate the x to flip horizontally, negate the y to flip vertically. Move things over if the line is off or above or down from our normal lines of reflection. We're going to do that twice because not only does it increase the distance here to move it, right, but it also increases the distance between A and that point, right? It's like we're moving the mirror further away from us. And so as the mirror moves further away, our other point's going to move further away, right? Mirror us is going to move further away from the mirror. So we end up having to do that twice. And then here it's just a matter of switching x and y. And here it's the same thing, except we're negating both, right? Both signs changed. -4 became +4, 3 became -3. Okay. Those are basic reflections. Complex reflections. This one I already have a video up on Classroom, so if you want to check that out, go there. Yeah, we're doing it in time. It's 1:30. I guess we could do some complex reflections. Let's do it. Put it all one-stop shop. So a complex reflection is a line that's not like any of the ones we talked about before. So flipping it over, not the y-axis, not the x-axis, not the y-axis moved or the x-axis moved, not 45-degree angle lines, not slope of 1/1. It's anything else. So what if we flipped over this line? So here's our line of reflection. I'm just going to make something up. Let's do, I think I did 3/2 in the previous video, so I'm going to do 3/4 here. So here's our line, y = 3/4 x, there's the slope. And I'll do -3 as a line of reflection. So if I were to graph that line of reflection, it'll look like this. Again, this is just me demonstrating how this works. That's what you're going to have to write about. And it looks like I start at -3 for the y-intercept, and then I'm rise of 3, run of 4. So from here, 1, 2, 3 up, and 1, 2, 3, 4 over. I can keep doing that, 1, 2, 3 up, and 1, 2, 3, 4 over to make sure my line is as accurate as possible. And I'll do it 3 down and 1, 2, 3, 4 over as well. So here's my line of reflection. We're going to be flipping points across this. And so what I'm going to do is I'm going to make up a point to flip over this. Let's do this point here, like this. Looks like it's at 1, 2, 3, 4, 5, 6, 7, -3. I'm going to flip that across this line. Now, all the others are simple reflections because the rules are pretty easy to figure out, right? They always follow the same pattern. This one is going to be different. It depends on what our slope is here, what angle we've already set. So first thing we need to do is we need to find the perpendicular line that goes across this, right? What angle do I need to take to make sure this hits it at 90? I can't just eyeball this because it's kind of a weird slope. So the perpendicular line that's going to hit this at 90 is going to be the same line but with exact opposite slope. So notice that the slope here is 3/4, and this one's the flip of that. 3/4 becomes 4/3, and then we negate it because it's obviously heading down into the right, whereas this one is heading up into the right. It's heading the opposite direction. So if I take this point and apply that slope down 4, 1, 2, 3, 4, and over 3, I can see where this line's going to end up. I'm also going to do the opposite, up 4, 1, 2, 3, 4, and then left 3. I'm going to keep doing that. 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3. And so I know A prime can end up somewhere on this line. the mirrored version of it is going to end up somewhere over here. I don't know where yet, but somewhere over there. Now, this is not the complete equation of the line. As you can see, I don't have a y-intercept at 0, right? I need to figure out what the y-intercept is here. And if we look closely, it looks like it's going to be a little bit above whatever that number is here. So a little bit more than 1, 2, 3, 4, 5, 6, a little bit more than 6 maybe. But to figure it out and be precise, what I'm going to do is this. I know 7, -3 is on this red line. So that means that when I plug in 7 to whatever this red line's equation is, what pops out for y is -3, right? So if I were to do that, -3 is y, 7 is x. The question is, what goes over here? This thing on the end, right? What goes here to make that so that 7 makes -3, right? Well, if we do some quick math, I can times by the top or divide by the bottom. I'm going to times by the top and get -28. And then I divide by 3 and get this. Doesn't simplify. Because I know 30 divided by 3 is 10. 28 divided by 3 is too close. It's going to be a number between 9 and 10. Just leave it like that. And then if I move this over by addition, I can figure out what b is. There are -9/3 in -3. Again, how many thirds are in 3 so I can get common denominators? Well, -9 divided by 3 is still -3. But now I can add these together and show that clearly this will be -9 plus 28 is 19. That's what b is going to be. So the number that goes here to make this work out so that 7 gets -3 is 19/3. And if you look, 18 divided by 3 is 6. 19/3 is a little bit more than 6. So that's where our line hits apparently, is 19/3 right here. Now we've got both equations. What we're going to do now to figure out where a prime is going to be is, because we know that this length is going to have to be the same as that length on the other side, we know that this is the middle between A and where our reflected point is, right? It's going to be the same distance here and the same distance here to wherever A prime is, right? We don't know where it is, but we know it's the same distance on both sides. So that makes this point the middle point. And what is this point? Well, this is the point where both our blue and our red line intersect. So where does this line and this line intersect? Well, it's the point where they both agree, right? 7 -3 is on the red line, meaning that when you plug in 7, right, you should get -3 for y. And it does, we made sure, right? This point is going to work for both the red and the blue line. So in other words, it's where both lines are equal to each other. It's where this y and this y are the same number. So if these two y's are the same, then I know if this equals y and that equals y, this equals that. If they both equal y, if 3/4 x minus 3 equals y, and -4/3 x plus 9/3 equals y, then I know they should equal each other. 9/3, right? 19/3 plus 19/3. There we go. So where do these equal each other? What's x going to be for this coordinate right here? Well, we can solve for x and figure that out. Terrible idea in real life, great idea in math. I'm going to get my x's together, and I'm going to move this over to do so. Now I've got my x's on both sides, 3/4 of an x and -4/3 of an x all together. It's now positive because I added it over. And then I'm going to add over the 3. 19/3 is already there. And then add over 3. Well, on this side, I've got 9/3 here. 9 divided by 3 is 3. When I add those together, I get 28/3. On this side, I need common denominators. So I'm going to make that a 12. And this a 12. 4 times 3 is 12. 3 times 3 is 9. So 9/12 is the same as 3/4. And you can check that, right? They both simplified to one another. Didn't change the problem, just made it look different. And then 3 times 4 gets me 12. So 4 times 4 is 16. 16 over 12 is 4 over 3. Same numbers, just different way of looking at them. And now I can see that how many 12s I have. I've got 25/12. To solve a problem like Maria, I know this is times 25 and divide by 12, so I can get rid of them in that order. Let's do that. I'm going to times by 12. And when I do that, I've got this. Divide by the top, times by the bottom, your choice. I'm going to divide by the bottom and get 4, and then times by the top. If I times by the top, that's going to be 120 minus 8, which is 112. 24, 26. I feel like that's wrong. This gets us 4. 12 divided by 3 is 4. Then we have 80 plus 32. Nope, that's right. And then I'm supposed to divide that by 25. So our midpoint is going to be at the coordinate 112 over 25, which is just under 5 in the x direction. And if you look, 1, 2, 3, 4, it's between 4 and 5 in the x direction. To find the y value is actually very easy because I already have some equations that say if you know what x is, plug it in here and get y. So I'm going to plug this value, my x value, into here and figure out what y is at that point. So if I do that, let me grab another piece of paper. I'm going to use this kind of as a cheat so I can see what's going on. Y equals 3/4 x minus 3, right? And I said my x value is 11 or 112 over 25. So now I can just do math to figure out what y is when x is 112 over 25. Well, we can divide or multiply in any order we want. I'm going to do 112 divided by 4. I know 100 divided by 4 is 25. I know 12 divided by 4 is 3, so that's 28. So I've got 3 times 28 over 25. It's 3 now, because I divided that by 4. And now I'm going to multiply the top by 3 and get 60 plus 24, which is 84. And then divide by 25. And that's as good as I can get it. So now I'm going to subtract 3. And the way I'm going to do that is I'm going to think of how many 25s, 25ths are in 3. 75. 75 divided by 25 is 3. So if I subtract those, I'm going to get 9 25ths. So when x is 112 over 25, y is 9 over 25, which is like less than 1, less than half, really, right? If you look, that dot is about less than half in the y direction. So there's our coordinate right here, 112 over 25. Always make sure to that these fractions, these coordinates make sense with your diagram. That's why you draw your lines extra carefully. That way you can check your work, make sure you didn't make a mistake back through here, getting common denominators or adding or subtracting things, maybe losing your x's, right? When you move that over, don't forget that's 4/3 x. When you plug stuff in, be careful. So far, everything seems to make sense. Gross numbers, but it makes sense. And then now what I'm going to do is I'm going to use midpoint formula to show where a prime is actually going to be located. Midpoint formula is the average of our x's and the average of our y's. And of course, to average something, you're going to add up and divide by the number of pieces. So midpoint formula says that the midpoint's coordinates, which for this problem, we actually know what they are. It's this. Are going to equal this coordinate, which is made up of adding our x's together and dividing by 2, averaging them, and averaging our y's. Normally, we have the 2 outside points that go here, this guy and then this one, and then we use this formula to figure out the middle between them, the average point, right, the middle point. But here, we already know the midpoint. It's 112 over 25, comma, 9 over 25. And we know only one of these points. I know 7, negative 3 is our starting point. So 7 for x, negative 3 for y. We don't know the other x or the other y. So all we have to do now is solve for x and y. I know that this right here is my x coordinate, which means it should equal this x coordinate, right? They're equal. So I know 112 over 25 should equal 7 plus x over 2. And this looks really crazy, but it's not so bad. We just double everything, right? Multiply by 2 and subtract 7 and we get our answer. On the other side, I know this equals 9 25ths. So again, I'm going to double everything, and then I'm going to add 3 to figure out this answer. So I'll show what that work looks like. When I double everything, I get 224 over 25, right? I have 112 25ths. Now when I double that, I have 224 25ths. And then I'm subtracting 7. How many 25ths are in 7? So I can get common denominators. Well, it's going to be 7 times 25 25ths. So that's going to be 140 plus 35, which is 175. And when I subtract those, I find out that x for my a prime is going to be add 25 to get to 200, add 24 to get to there. So it's going to be 49 25ths. Over here, when I double everything, much easier math, 18 25ths. When I add 3, that's the same thing as adding 75 25ths. So altogether, I'm going to get 75 plus 10 is 85, plus 8 is 93 25ths. So in total, A prime is going to be at 49 25ths. That's just under 2, right? 50 divided by 25 is 2. And 93 over 25, which is just under 4. So just under 2, just under 4 is where A prime is going to be. So just under 2 in the x direction. So I'll go like right there. Zoom in. Just under 2. And then just under 4. 1, 2, 3, and then just under 4. It looks like to be on our line. That should be about it. So just under 2, which is 49 over 25. And just under 4, which is 93 over. And there's the reflected point. The same distance on both sides and completely perpendicular to the line of reflection. Like I said, this is a lot of stuff, right? First, we got to figure out where or what the equation of this red line is. And we did that by flipping and negating the slope. And then we plugged in the point that we started with that's on the red line to figure out what this has to be, right? We plugged in 7 and negative 3, did math, and figured out B had to be this, 19 over 3. And then we set these two equations equal to figure out where they intersected. So we set them equal. We got our x's together and got common denominators. We found the x. Then we went back and plugged that x into here, one of the equations. And then we did math and got the y. And that got us where they intersect, the midpoint. And then we used midpoint formula with that knowledge. We knew the midpoint. We knew one of our coordinates here. And then we set it up and knocked it down, right? We got the x and the y for A prime. That takes us through number 12. The good news is that's definitely the hardest part of the entire thing. And the calculation, I'm not so picky on. So double check your calculation. Try to make it as right as possible. But as long as your ideas are good and you're able to explain what's going on and why we're doing the math that we're doing, you know, why are we setting those two equations equal? Because we want to figure out where the intersection point is, right? So we can use the midpoint to flip it. Why are we flipping and negating the slope? Because that's how you find perpendicular slope, right? It's going to be the exact opposite angle. If you can explain that as you're going through doing the math, if you make a couple of arithmetic errors, it's no big deal. No big deal at all. So don't be afraid of it. But just go back and check your work. It'll make you less frustrated. And if you need help, please contact me. So for 13, 14, 15, 13 and 14 are about rotations, and 15 is about dilations. So 13 and 14 I'm going to do all in one go. And rotations are actually really simple. And dilations are even easier. So a basic rotation is when the center that we're rotating around is 0, 0. And if we have a triangle, again, I like using triangles because they're really simple. More points means more work. So fewest number of points is a triangle. And what we're going to do is basically we're going to draw an L between our center and our point, and we're going to rotate that L however much we want. So if I wanted you to rotate this 90 degrees counterclockwise, that L is going to rotate this way. And you'll notice that what once was the horizontal part, right, this part right here, is now going up and down. So it's now treated as vertical. And what once was vertical is now going to be horizontal. So our rule for a 90-degree counterclockwise rotation is take your x and y, and you're going to flip them. What once was a horizontal part is now being treated, the x is now going to be treated as a vertical part. That's why it's in the second spot. The vertical part, the y, is now going to be treated horizontally, so it's going to go in the first spot. You'll also notice that we went from positive x to still positive after we're done, right? It's just going up now. And a positive y to a negative y, because it's heading to the left. So instead of going up, now it's going to the left. So you can see that the y changed its sign. So there's our rule. the y is going to change its sign and be treated as a horizontal value. If we'd gone the other way, going down this way, you would have drawn your L like this. Again, x would now be thought of as vertical, but you'll notice it's going down. And the y value is going to be thought of as horizontal, but this time it's still positive, right? It's heading to the right. So our rule for a 90-degree clockwise is take your original coordinates and do this. Looks like x and y are going to switch spots, right? Because what was once horizontal is now vertical, and what once was vertical is now horizontal. And it looks like the x changes its sign. It becomes negated. There's our rule. You can imagine a 180-degree rotation would just be two 90s in a row. So if I applied this again, rotating this way, let's say, for 180, the first 90-degree rotation gets my x here, right, from horizontal to vertical. And then afterwards, it's going to make it go horizontal again. And then this vertical part is going to go horizontal, and then it's going to point down after we're done. So you'll notice that x here is now negative. It's going to the left, where it was positive before. But it's still horizontal, right? This part and this part are both going to be horizontal. Ignore this x right here. They're both horizontal, but one's going to the left and one's going to the right. So x is still going to be treated like a horizontal. Doesn't matter which way you turn it. And y, the vertical part, is still going to be treated as a vertical part when we're done. But again, you should notice that once right and up, now we're going left and down. So both are going to get negated. But with no switch, because horizontal stays horizontal, vertical stays vertical. For a 270, you can imagine that it's this turn all the way over to here. 90 plus 90 plus 90 is going to get you 270, which is the same as just 90 this way. So a 90-degree clockwise is the same as 270 counterclockwise. And a 90-degree counterclockwise is the same as 270 clockwise. Those are all our basic rotations. The advanced rotations are actually less to describe. It's just what happens if the center isn't where we're rotating? What if, or if 0, 0 is in our center? What if the center is somewhere else? Well, the rule's going to look more complicated. But how it works isn't that crazy, really. So let's pretend our center's here. This is 3, 1, 2, 3, 4, 5. And we're going to rotate our object around here. Let's start it here. Point A, point B, and point D. A is at -2, 1, 2, 3, 4, 5. B is at 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 7. And D, that top point there, is at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's just see what happens under rotation to these points. Well, if I draw an L here and I end up here, we know B prime is going to go, instead of right and up, it's going to go down and over the same amount. And you'll notice our coordinate is now 1, 2, 3, 4, 5, 1, 2, 3, 4. So it's not as easy to see what's going on here. A, instead of, since I'm going this way, is going to end up here. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And the coordinates here that we get are going to be really weird. They're going to be strange. This is -2, 5, and what it ends up on, this one ended up at 5, 4 for B prime. A prime is going to end up at 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, it's not really obvious what's happening here. Remember, the same rule has to apply to all, so you can't just add 1 and subtract 3, because adding 1 and subtracting 3 wouldn't get you the same answer here. So what's going on, right? This is a very strange rule, it looks like, but it's actually very simple. What we're going to do is we're going to push everything. We're going to slide. We're going to translate everything down so that C ends up on 0, 0. Because once C is on 0, 0, we can treat this problem like a normal problem. So everything's going to get pushed, including the original triangle, however much it takes to get C to here. Well, how much does it take to get C to there? Well, if you look, it looks like we need to go 3 to the left and 1, 2, 3, 4, 5 down. The first thing we're going to do is we're going to go 5 down and 3 to the left. We're going to translate it, right? 5 down. Whoops, did I screw that up? I think I goofed these, didn't I? We're going to go 3 to the left, so minus 3 from the x, and then 5 down, so minus 5 from the y. Get there. And again, this is the coincidence that they're both negatives. I just looked where I needed to go, and I need to go left and down. Left and down is negative. Sometimes your center might be over here, and we have to go right and down to get there. Depends. So now that I've done that, I can treat it like normal. And for this problem, we wanted to do a 90-degree clockwise rotation. So I know my 90-degree clockwise rotation rule. It's flip them and negate the second. So what I'm going to do is I'm going to take this, and my real rule is going to be these two flipped. I'm wrapping this in parentheses because this is the first thing I did, right, as I moved everything. There's my movement. I flip them, so x and y are in opposite spots. And then I'm supposed to negate the x, right, the second value. So there's my rotation. And so what we've done is we basically moved everything here, rotated it as if it was centered here, and now we're going to push everything back to get it in the right spot. So now I'm going to undo what I did before. Before I subtracted 3 from the x and subtracted 5 from the y. And so what I'm going to do to push that back is I'm going to add 3 to the first value, and I'm going to add 5 to the second value. And that's going to push everything back to the right location, and that's going to be my rule, which is pretty complicated. That's why it's hard to see what's going on here. So just be careful that when you see minus 3 from the x and minus 5 from the y, you don't think, oh, I add 3 to the x to add 3 to the y, and you see an x there and add 3, and a y there and add 5. Notice that these are opposites, and the reason for that is because when we subtracted 3 from the x, what we really did is we subtracted 3 from the left coordinate, right, the left side coordinate. So when we add 3 back, we want to add it to the left side coordinate. And we subtracted 5 from the right side coordinate. So when we add 5 back, we're going to add it back to the right side coordinate. So don't just look at these letters right here. Make sure you think about which side's getting added to. We're going to add 3 to the left and add 5 to the right. That's where these blue numbers come from. And there's our rule. And what's useful about this rule is that you can plug numbers into it and get the correct coordinates for the rotation. If you had lots more points than this, like pretend you had to like rotate a dodecahedron 12 different points, it would be really annoying to draw all your L's and figure out where it goes. And so having a rule that you can just plug numbers into, a formula basically, will save a lot of time. This is kind of a gross looking formula though. It's nice because it shows where everything comes from, and I do want you to explain where the red numbers came from, the blue numbers, why the x and y are switched, why we negated that. I want you to explain all that. But for plugging in stuff, this is kind of nasty. Y minus 5 plus 3 is really just y minus 2. So I'm going to do that. That's way easier to plug a number into. And then this is negative version of x, is that minus sign. And then the negative version of negative 3, because that minus sign makes it positive 3. And then we're supposed to add 5. So there's our second part of our rule. The second number is going to be negative version of x plus 8. So if I apply that, for instance, to D, this says to find the first number, I need to take y minus 2. So y is 9, and if I subtract 2, I get 7 for D prime. And then to find this number, the second number, I need to take the negative version of x, which is still 0, and then add 8. So D prime should be at 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. And if you look, here's our original shape. And here is our new shape, which has clearly been rotated 90 degrees clockwise around this guy. Right? It's kind of rotating around that C. So all I need to see is one demonstration of this. You pick whatever rotation you want and show me the actual rule and explain the parts. And if you want to, simplify it and then apply it, right? Show me the graph as well. So that's rotations. And then we're almost done. We have dilations. Now, dilations are very similar to rotations. So if you're not super comfortable with rotations, this will be a second shot at looking at them. And then if you are super comfortable with rotations, then this will be a breeze. Dilations, remember, make things smaller or bigger. So we're going to be multiplying by a scale of like times 2 or times 3 or times a half or whatever. And they're also going to have a center, just like dilation. So if the center's at 0, 0, it's very simple, right? You want to double everything? Great. Your rule is going to be times 2 to the x times 2 to the y. If the center isn't there, then again, much like dilations, like if the center was negative 3, 5, all we're going to do is push that center back. So let's say that my shape I want to dilate, my image I want to dilate is, let's do this. Here's this triangle. And I actually want to cut it down in size. I want to have it both in the x direction and the y direction. So my rule normally, if this was at 0, 0, would be just a half times x, half times y. But because this c is not at 0, 0, first we're going to push everything in such a way that c ends up on 0, which is just a translation, which is like the easiest thing to do, right? So the first thing we're going to do in our rule is we're going to push everything back in this example. We're going to push it 3 to the right and 1, 2, 3, 4, 5 down. So to do that, I'm going to go 3 to the right. That's plus 3 to the x. And 5 down is going to move everything 5 down, so minus 5 to the y. And that's the first thing I did, was push everything. So I'm going to wrap that in parentheses to make sure algebraically that happens first when I plug in numbers. So now everything's been pushed in such a way where c is on 0, 0, and the triangle's kind of over here somewhere, right? And now I'm going to apply my dilation. I want half of everything, so that's very easy. I will simply multiply everything by a half. Half times all that. And now our triangle has been shrunk by half in every direction. So everything got pushed, and then we're shrunk. So now we did our dilation. And now, to figure out where it actually belongs, like the real dilation around the center, we're just going to push everything back, and that'll resituate it. So to push everything back, well, I need to go 3 to the left. So that means minusing 3 from the x value. And I need to go 5 up to go from here to here. So I'm going to add 5 to the second value, the y value. And there's my messy, convoluted rule. And if you want to apply that, here's point A. Point A looks to be at 1, 2, 3, 4, 5, 6, 7, 8, comma 3. Negative 8, comma 3. And if we apply that rule, just like before, I'm going to simplify this. This is a half of x. Half of 3 minus 3 is going to be negative 1.5. And then here, half of y minus half of 5, right? That's negative 2.5 plus 5 is going to be plus 2.5. So here's my simplified rule. I like this one again because it shows, it's easy to see where these numbers came from, right? We undid this, then we halved everything, and then we took this, which moved it back. But this is much easier to plug numbers into. If I take this, it says to find the first number here, I need to take half of x, so that's negative 4, and subtract 1.5, so negative 5.5 will be where a prime ends up off the x value. And then here, we need to take half of y to figure this out, so that's 3 halves, or 1.5. And then we're going to add 2.5 to it, so that's going to be 4. So that's where a prime is going to be, negative 1, 2, 3, 4, 5.5, comma 1, 2, 3, 4. And as you can see, a prime not only is going to be part of a smaller triangle, but it's also got closer to our C, our center, right? And it used to be this far away, now it's this far. It's half as far away as it was before. So not only do things shrink, but they move closer. And if we were to make it bigger by doubling it or something, it would have also moved further away by that amount. I can do this for B, which is this point here, and this point here, D, just to show what happens when we plug this in. So it looks like this is negative 8, so that's negative 9, 4, 5, 6, 7, 8. So negative 9, comma 8. And D is at 10, 11, 12, so negative 12, 5. And when we apply this rule, I need to take half of x, so negative 4.5, and subtract 1.5, so that's negative 6. And then I'm supposed to take half of this, so 4, and add 2.5, 6.5. For this one, I need to take half of it and get negative 6, and subtract 1.5, so negative 7.5. And then here, half is 2.5, and if I add 2.5 back, I get 5. So negative 6, 1, 2, 3, 4, 5, 6, comma 6.5. 1, 2, 3, 4, 5, 6.5. That's where B prime is. And then D prime is going to be negative 7.5 comma 5. So 1, 2, 3, 4, 5, 6, 7, 8. Here's 7.5. 1, 2, 3, 4, 5. And there's our triangle, half as small and half as far away from C as before. When you multiply by the same number here and here, what it does is it keeps your image proportional, meaning that if you were to connect all the dots before and after, the lines that these would kind of run on, these rails, I like to call them, are all going to intersect at your center of dilation. And if we were to triple both the x and the y, it would push it out further in this direction, and all the dots would be on these lines. If we were to cut it by a quarter, it would be shrunk even closer and be in here, right? And we call that being proportional, because what will happen is it'll be the exact same triangle, as you can see between our original triangle and our dilated triangle. It's the exact same triangle, it's just the size has changed, right? And this kind of goes back to our Pythagorean theorem proof. Remember when we multiplied everything by a and all the angles stayed the same, right? And that was as long as we multiplied everything by a, right? And if we multiplied everything by b, all the angles stayed the same. If we multiplied everything by c, all the angles stayed the same. So whatever number you multiply the triangle by, here in green, as long as you do it to both, right, do it everything the same, the angles will all stay the same, meaning that you'll end up with the exact same triangle, just smaller or bigger. If we were to make different numbers here, like if we were to have doubled this one and maybe multiplied this by -3 instead, it would not have been proportional. It wouldn't have stayed on these rails, and it would have stretched the angle. So we would have gotten a different triangle that was much bigger, right? Definitely bigger because we're timesing by 2 and by 3. Twice as much in the x, 3 times as much in the y, so it's going to be a pretty tall triangle. But it's going to be a completely different triangle because the angles are all messed up. Also, this negative here, what it's going to do is it's going to flip things vertically. And that kind of goes back to our basic reflections, right? When we had a rule like this, when the y was negated, what happened was it flipped vertically. So that negative here, when we're multiplying, is going to flip it vertically. So not only is it going to be 2 times wider and 3 times taller, but that 3 times taller is actually going to flip the triangle down this way. So it's still going to be 3 times as tall, but it's going to be facing the opposite direction. So if I were to do that to this, what would happen is that B and A would kind of switch spots, because B would now be on the bottom and A would be on top because we're flipping vertically. And of course, B and A would be really far apart because they're times by 3. And then A and D and A and B would be sort of far apart because it's been times by 2 in the x direction. So that's dilations. I need you to explain where these different colored numbers come from. Make up your own example for what to do. I need to see what happens when you multiply by a fraction. I need you to explain what happens when you multiply by a negative and what happens when the numbers are different versus when they're the same. Proportional versus completely different triangle, right? That's all I need for this entire semester, and it looks like I've explained it in basically 2 hours with a bunch of interruptions. So everything that I taught for, 45 minutes, 4 days a week, since we had 1 day off in the middle for Wednesdays, can all be condensed down to 2 hours of really rushed review. If this is your first time watching this, I'm sure you're confused about what's going on and wish I had gone slower. And that's why we do this 45 minutes, 4 days a week over, 16 weeks, so I can do this slower. But if this is not the first time you've watched this, hopefully this speed wasn't too fast for you and you can go back and rewind, do whatever you need to do to watch this again. And this will refresh and help you fill in the gaps for what you might have missed. Nobody showed up for the live stream today, which is totally understandable. It's Christmas break. I know I don't want to be here. So you kind of missed the opportunity to ask specific questions, but I will be available via email and anything else that you need if you need help. So I don't expect this to fill in all the blanks and help you 100%, but I do hope this gets you most of the way and ends up saving you and myself time. That way we can start enjoying our break a little bit more and leave this stuff behind and be ready for next semester. I'll be available, like I said, by email or whatever. And if